Hello everybody, how are we doing? Today we're going to start Chapter 8, and Chapter 8 is about rational expressions, equations, and functions. And we are going to skip section 8.1. We usually only spend a few minutes on it, just with a warm-up. We're going to skip sections 8.2 and 8.3. We always skip those and we save those for pre-calculus. So we're going to focus this month on 8.4 through 8.6 and an extension, as well as going beyond the book to a topic called partial fractions. So let's talk about what do we mean by rational expressions, rational equations, and rational functions. Well, think about rational numbers. We've talked about rational numbers before. Rational numbers are numbers that you can write as fractions of an integer over an integer. So rational expressions are also going to look like fractions, but they're going to be a polynomial over a polynomial. For example, x plus 1 over x squared minus 5. Polynomial expression over a polynomial expression. If it's a rational equation rather than expression, it will have an equal sign in it. So maybe that would be x plus 1 over x squared minus 5 equals either just a number or another rational expression, like perhaps it equals 1 over x plus 2, and we would be solving for x. And then what's a rational function? A rational function would be something like f of x equals x plus 1 over x squared minus 5, and we would be looking to graph it and find the features of the graph. Now, we're not going to study rational functions this year. We're saving that for next year. So today we're going to start focusing on rational expressions, and we're going to start by thinking about how to simplify them. So first, let's think about how we work with rational numbers and how we simplify them. Let's take the fraction 3 over 12, and let's say we want to simplify it. So what we do, we might not even realize that this is what we're doing, but what we learned to do long ago was factor the numerators and denominators. So the numerator is 3, it's prime, and the denominator is 3 times 4. You could think of the numerator as 3 times 1 if you want to. And then what we do is we cancel the 3's. Well, why do we cancel the 3's? It's because 3 divided by 3 is a special form of 1, and 1 times 1/4 is just 1/4. So all we have left is 1/4. So we like to say that the 3's canceled. We also could say we divided the top and bottom by 3, but the whole reason for doing that is because those factors canceled. So the key to simplifying expressions, rational expressions, is going to be to factor and cancel, or factor and reduce. Multiplying and dividing we'll talk about more later, not this lesson, as well as adding and subtracting comes later in the month. So each time we learn a new skill with rational expressions, we should think about what we did with rational numbers, and that will help us. Okay, so let's figure out what notes number we're on for today. I'm sure you can look in your notebook and figure that out. I don't actually know. I should have looked that up. And we're going to work through 7 examples of simplifying rational expressions. Remember, the key is that you want to factor, and then you can cancel or reduce factors. You can't cancel or reduce unless you have factors. So number 1 is already factored for us. And hey, feel free anytime to pause the video, to write the problem down, or to work the problem out and then resume the video when you're ready. So notice that number 1 is already factored, so we can cancel the factor of x plus 1 from the top and the bottom, and what we have remaining is 2 over x plus 3. So there's our answer. Let's take a look at number 2. Now, it's not ready to reduce or cancel yet because it's not factored. Remember, factored means just a product of things multiplied together. So what could we do to factor the numerator? Well, we could factor a 20 out of both terms, and that would give us 20 times 2x plus 1. And how about that denominator? We could factor a 10 out of both terms, and we would have 10 times the quantity x plus 3. Now you could think of, even if you don't write it, you could think of the numerator as 10 times 2 times 2x plus 1. and then the denominator is 10 times x plus 3. So notice that we have a factor of 10 on the top and a factor of 10 on the bottom, and the top is just factored something times something times something. The bottom is just factored something times something. So we can cancel the 10s, and then our answer is 2 times the quantity, oops, try that again, 2 times the quantity 2x plus 1 over x plus 3. Is it necessary to distribute the 2 when you write your final answer? I don't think so. I think it's perfectly fine to leave it like that. You could distribute it and it's not wrong, but if you don't, it's not wrong. Okay, let's move on to problem number 3. So notice that the denominator is already factored, and I suppose we could factor the numerator if we want to into 2 times 2, but notice that you don't have any common factors on the top and the bottom. So nothing's going to cancel or reduce or divide out, whichever wording you like. Therefore, the original expression was already in its simplest form. So what we can do to answer this is either to just go ahead and circle the original expression, or to say that it's already simplified, or something like that to indicate that you looked at it and you know there's nothing you can do. Okay, let's take a look at number 4. Looks like with number 4, we could factor the denominator. So remember how to factor a difference of squares. You factor that into conjugates, and they would be x plus 4 times x minus 4. Okay, well notice that your whole numerator is a factor of x plus 4, and you have a factor of x plus 4 on the bottom, so you could cancel those. It looks like there's nothing left on the top, but we don't want to think of nothing as 0. You can think of the numerator as x plus 4 times the invisible factor of 1. So what we have left is 1 over x minus 4. Okay, we have 3 more examples. Here's number 5. So remember, you cannot do this. X squared, cancel, cancel. Why can't I do that? Because we have to only cancel factors, things that are multiplied, not things that are added or subtracted. Let me show you an example of what would happen if I canceled things that are added or subtracted. Here's just a really simple example. Let's say I had 2 plus 3 divided by 2 plus 4. Well, it should be 5/6. I think we could agree if you simplify it properly. However, what if I cancel the 2's? Now I get 3/4. Well, 3/4 is not right because we knew it should have been 5/6. So that's just a way to remind you that you can't cancel things when they're added or subtracted, only when they're multiplied, because what you're canceling would be special forms of 1. Okay, back to the problem. Let's factor the numerator. It factors into x minus 3 times x plus 1. Let's factor the denominator. It factors into x minus 3 times x plus 2. Well, would you look at that? We have a common factor on the top and the bottom, x minus 3. We can go ahead and cancel that. What do we have left? X plus 1 over x plus 2. Okay. Next one, number 6. So, well, we can still factor the top, but remember there's all different kinds of factoring, and one kind of factoring is just pulling out the greatest common factor, the GCF. So looking at the numerator, it looks like we could factor out a 2x from both terms, and that would leave us with 5 minus x. And then the denominator could be factored into 2 binomials, x minus 3 times x minus 5. Okay, now let's take a look at this. We have 5 minus x, we have x minus 5. Those are not the same, so we can't just cancel them. But do they have a relationship? Let's put some numbers in there. What if it was 5 minus 2 and 2 minus 5? 5 minus 2 would be 3. 2 minus 5 would be negative 3. They would actually be opposites. And what happens when you divide 3 by negative 3? You get negative 1. Does that always happen with opposites? Let's take another case just to convince ourselves. What if it was something like 7 minus 12 over 12 minus 7? That would be negative 5 over 5, and that would be negative 1. So if you have opposites, you can reduce it to -1. Usually we cancel things because it gives you a special form of 1, but opposites divided are a special form of -1. So as long as you leave a -1 there, you're good. So what do we have left? We have the opposite of 2x, or -2x, over x minus 3. Now, you could leave your answer like this and it would be perfectly fine, but what you might notice sometimes if you're looking up an answer is you might notice something looks different. You might notice something like this, 2x over 3 minus x. Do you see what they did? They just multiplied the top by -1 and the bottom by -1 to get this answer, which looks a little bit nicer than the previous answer because it doesn't have as many negatives in it. So these answers are equivalent to each other, and it wouldn't matter to me which answer you gave. That is supposed to say equivalent. A little hard to read there. Okay, we are down to our final example, and I thought it would be fun to throw in some extra kinds of factoring that we don't see every day. So look at this numerator, 8 minus x cubed. Do you remember what we call that? We call that a difference of cubes. And do you remember the formula for factoring a difference of cubes? If you have a cubed minus b cubed, remember how to factor that? That would be a minus b times a squared plus ab plus b squared. I know you memorized that once upon a time, way back in a previous chapter, and it's going to pop up again every once in a while, that and the sum of cubes. So let's factor 8 minus x cubed. 8 is 2 cubed, so 2 cubed minus x cubed would be 2 minus x times 2 squared 4 plus 2 times x plus x squared. So that's our numerator, 2 minus x times 4 plus 2x plus x squared. And then let's take a look at that denominator. Hey, do you remember how to factor things like that? When you have those 4 terms like that, you could factor by grouping. So you could factor an x squared out of the first 2 terms, and that gives you x squared times the quantity x minus 2. And then you could factor -5 out of the last 2 terms, and that gives you -5 times x minus 2. And then the next step in that is to write it as x squared minus 5 times x minus 2. So the x minus 2 came from this common factor, and then the x squared minus 5 came from what was left in the problem. So that's our denominator, x squared minus 5 times x minus 2. Now, can we cancel or reduce anything? Well, hey, look again, we have opposites. We have 2 minus x on the top and x minus 2 on the bottom. Can we cancel opposites? Well, kind of. We can if we leave a -1. A number divided by its opposite is -1. So our answer is going to look like, possibly look like, the opposite of the entire numerator that we already had over x squared minus 5. We could leave it like that with the negative on the outside, or we could distribute the negative through the numerator, or we could distribute the negative through the denominator and just write it like this. The denominator would be written as 5 minus x squared if you distribute the negative through it. These are equivalent. It doesn't matter to me which one you give as your answer. You just need to know that they're equivalent. Okay, that's the end of today's lesson. You have this homework assignment. I'm calling it 8.4 Part 1 because we only did part of 8.4. The other part we'll do next time. And so what I want you to do is do these homework problems, but you don't need to turn them in yet. Wait to turn them in until we do 8.4 Part 2, and then we'll just put them together as one assignment. Make sure you show your work, check your answers, and if you don't have a book, you can use the attachment on Google Classroom that has all the problems. It also has all the answers. So notice that a couple of these problems are evens, so you're going to need to check those answers anyway. And then, of course, let me know if you have questions. All right, thanks everybody.